All right, so yeah, welcome everybody to another session of the diffusion chronometry seminars that we've been having. And for those of you who've been here before, we've usually had this system of 2 talks and then combined discussion. Now, this time around, with the summer coming up, we have only 1 talk, so the format would be more conventional, so a talk and then questions and discussion following that. Now it's my pleasure to have John Blundy here today. John is a name that probably, is to this particular audience doesn't need to be introduced, but I'll just go through the motions of doing that nevertheless. So John studied at the universities of Oxford and Cambridge, and then as far as I can tell, or I've known him, spent a long part of his career working at the University of Bristol, and is back in University of Oxford for the last few years. Now, the thing that occurs to me when I think of John is how versatile he is, because he's obviously here today to talk about magmatic systems and igneous systems and plumbing systems and things like that. But if you look up his citations, his most cited work would actually be thermodynamic mixing models of amphibole or something. And then the other body of work for which he's known well beyond igneous petrology actually is his work on element partitioning and the lattice strain model that goes all the way into sedimentary systems and then environmental systems and so forth. But yeah, he's here today to talk about igneous systems, of course. He has done many important contributions, but some things that have shaken up conventional views of igneous petrology. One thing that really struck me and I find really funny is that he showed that magmas can actually get hotter when they crystallize. So I thought that was a pretty cool result. And our current views of the magmatic plumbing systems have been influenced a lot by work he has been doing with others, in the group in Bristol with Kathy Cashman, with Steve Sparks and others. So today is going to talk about petrology to constrain magma source depths and ascent rates in volcanic arcs. That's a really important question for all that we do. And it becomes particularly important in what he's working on more recently is the role of igneous systems connected to ore deposits, and actually green mining is one of his current interests from what I can tell. So yeah, rather than listen to me talk, I think I'll let John take over here. John, very glad to have you here.
Right, well, thank you very much for inviting me, and thank you for that generous introduction, Sumit. If you stop sharing, I'll start sharing, and then we'll get going. So let me just check you can all see that okay?
Yeah.
Yeah. Okay. So, well, as I say, thank you very much for inviting me. I'm aware of your seminar series that's had a lot of very interesting presentations over the year or more it's been running, and I thought I'd share today some work. It's quite mature in that Ralph Doman, who is in the audience, will recognize some of this from his time in Bristol. I like to think that the maturity has reached a point that I can actually publish it at some point, but this is the culmination really of about 33 years work on this very fine looking volcano, Mount St. Helens in the Cascades range of the US. And using a combination of petrology and geophysics and experimental petrology and then subsequently diffusion, I think we were able to say quite a lot about the plumbing system beneath this volcano and the timescales on which the various petrogenetic processes take place. Okay, so let's advance the slides. Oh, I should mention a couple of other co-authors on this, Lieg Melnik and more recently Gregor Weber who are in Grenoble and Bristol, respectively, as well as Ralph. So the objectives here are to try and establish whereabouts andesitic magmas, andesitic dacitic arc magmas are generated. Where are they actually manufactured within the crust? And then over what depth range do they then degas and crystallize? Are they crystallizing deep or shallow or somewhere in between? How fast do they travel from the source region to the summit prior to eruption? Do they stall on the way, or is it one journey all the way from the source region? If so, how fast is that journey? And then can we link these petrological observations to geophysical monitoring signals so that we can better prepare for an impending eruption, because we can see a magma system becoming rejuvenated, and we can then interpret geophysical signals within a petrological geophysical framework. As I say, I'm going to use the iconic 1980 to 86 eruption of Mount St. Helens as a natural laboratory because it is unusually well constrained. So I think you probably all know where Mount St. Helens is. Here it is in Washington State. This is the Cascadia subduction zone. The eastward subduction of the Juan de Fuca plate gives rise to volcanism from Northern California right up into British Columbia. And Mount St. Helens is in many ways a fairly typical arc volcano. Its chemical composition in recent times, 1980 to 86, and indeed 2004 to 2006, shown by the red squares. But over its history, over 40,000 years, it's actually erupted a whole range of magmas, from really quite mafic basalts out here to more evolved rhyodacite. So I'll talk about Mount St. Helens as a dacite, but it really straddles the silicic andesite dacite boundary at 63% silica. Other components of the Mount St. Helens system that I'll be talking about are very evolved liquids that aren't erupted as lavas or tephra, but they occur as either matrix glass in dome rocks or pumices, or as melt inclusions. And those are these symbols out at 70 to 80% silica, normalized to 100%. So this is just a refresher on the 1980 to 86 eruption. This eruption actually took place in the year I became a geology undergraduate, so I have a particularly fond attachment to Mount St. Helens, if for no other reason than that. And prior to its eruption, it was a rather fine-looking stratovolcano. Here it is sometime in the 1970s, his Spirit Lake in front of it. And the eruption itself began on the morning of May the 18th, 1980, with first this lateral blast triggered by a landslide. The volcano had been swelling since the spring of 1980 and becoming unstable. And the blast released pressure on a shallow body of magma called the cryptodome. And eventually that decompression event affected magmas stored more deeply, leading from the lateral blast to a big Plinian eruption column. Over its subsequent 6 years of that eruption, almost all of the magmatic activity was associated with dome-forming eruptions. So in the crater formed by the explosion and the lateral blast, the collapse, a dome grew, and this dome grew to various heights. It periodically collapsed, certainly early on, to produce pyroclastic flows, these green symbols here. And when I was last there in 2003, it looked like this. It did erupt again in 2004 to 2006, producing some quite spectacular spines, similar composition to this 1980 to 86 eruption, and probably vestigial magma that was pushed out like the congealed end of a toothpaste tube. I'm only going to talk about the 80 to 86 eruption. So what's great about working on Mount St. Helens, as well as this wonderful volcanological and petrological record, and a lot of samples and archived material, there's an increasingly detailed body of geophysical images. So back in '92, this is Jonathan Leese's work, showed that the magmatic system is really quite vertically elongate. He characterized it with earthquakes. They can be better located now, but these are the earthquakes he located back in the 1980s and early 90s. And he defined the earthquakes, you reckon the earthquakes define the margins of magma bodies. So this is magma ascending from some deeper source region, inferred to be deeper than about 15 kilometers or so, according to Lees. And where you don't have earthquakes, in these aseismic regions, he suggested that magma was stored and there were little pockets everywhere from 10 or 12 kilometers up to relatively shallow depths beneath the edifice. In terms of the electrical conductivity, Mount St. Helens lies above something called the lower crustal conductor, which is an electrically conductive anomaly that extends all the way along the Cascades Arc at a depth of about 15 to 20 kilometers. And its conductivity tells us that it's a body with partial melt. So it's not fully molten, it still transmits shear waves, but the conductivity tells us there's probably an intergranular conductive water-bearing melt phase. And the lower crustal conductor connects to surface volcanoes. Here's Mount St. Helens, Mount Adams, Mount Rainier, and so on, with these vertically extensive tendrils, if you like, that actually don't go straight up. You can see here the tendrils wrap around SLB, the Spirit Lake batholith, larger blocks of relatively rigid plutonic rock. The magma ascends around the margins of those blocks. So this, one would imagine, is perhaps where dacite magmas are generated, and then these are the pathways that they follow on the way to the surface. And these pathways, again, we see earthquakes with black dots, and these white dots are actually long period earthquakes, probably related to fluid release. In terms of seismic velocities, we see regions of reduced P wave and S wave velocity that coincide with the lower crustal conductor. Here's the summit of Mount St. Helens. Volcanoes, VT earthquakes, volcanotectonic earthquakes extend down to about 10 kilometers. And out here, we're getting some of the longer period earthquakes. So this region here of 5+% velocity reduction is the mushy region that would be considered to be the source of the dacites. This is where they actually acquire their chemical character. And the point really here is that magmatic systems are vertically extensive. They cross a significant depth range within the crust. The MOHO here would be about 40 kilometers. So in terms of the experimental petrology, this is some old work that I did with Kathy Cashman 20 or so years ago. If we imagine a vertically extensive system, magma is going to leave its source and experience decompression as it ascends. As it decompresses, it loses volatiles. And the loss of volatiles means that it becomes progressively undercooled as it ascends. So this is a phase diagram for water-saturated conditions on the Mount St. Helens dacites. And we see here, this is the liquidus. And the liquidus phase is plagioclase at low pressure and amphibole at high pressure. And if we imagine the magma ascending from somewhere, say 15 kilometers down here up to the surface, if it ascends sufficiently rapidly, say near adiabatically, it doesn't cool a lot, it acquires an undercooling relative to the liquidus that grows as decompression proceeds, meaning that early on we have a small undercooling. We tend to crystallize phenocrysts because growth rate dominates over nucleation. As we get to shallower pressures, the undercooling becomes greater and we tend to grow microlites. And that explains this sort of dichotomy of crystal sizes: big phenocrysts, or variously sized big phenocrysts, often with very complex zoning patterns, and then a matrix. We've zoomed in here, that's 100 microns, a matrix made up of interstitial glass and lots of rather rapidly grown swallowtail or hollow plagioclase microlites, and then lots of vesicles because of the degassing. And actually, if we just look at the dacites themselves, the erupted dacites, we see that they're made up of about 35 to 40% phenocrysts in a matrix of glass or glass plus microlites. In the Plinian eruption, the really big phase on the morning of May the 18th, there are no microlites, telling us that we accomplished this final part of the ascent so fast that crystallization couldn't occur. And this image here from Matt Rutherford's really excellent piece of work in 1985 shows how the amount of melt, that's orange, decreases and the crystal phases increase as the pressure drops. at constant temperature. So this raises the possibility of magma crystallization essentially isothermally, giving rise to the phenocryst population. And we see the phenocrysts are dominated by plagioclase in blue at shallow pressure and orthopyroxene, but at higher pressure, where amphibole is stable, the early phenocrysts would be amphibole. So we see this overall evolution from 240 MPa to shallower depths can be described entirely by decompression crystallization. There's no need to invoke cooling as the cause of crystallization. So decompression provides the undercooling to drive the crystallization. Deep in the system, the undercooling is small, so we get big crystals dominated by growth. Later on, the undercooling is greater, so we tend to get microlites. And of course, amphibole that was stable here stops being stable at some depth, so we get resorption of the amphibole, early formed phenocrysts. And we would expect melt inclusions trapped in any of these phenocrysts, amphibole, plage, OPX, to record a story of magma ascent, degassing, and crystallization. So I've analysed a lot of melt inclusions from Mount St Helens. I think there's more than this, but there were 350 when I made this plot. And this is a plot of the water content of the melt inclusion versus the silica content of the melt inclusion. So obviously differentiation, crystallization of plagioclase, amphibole, pyroxenes, and so on, drives us to the right, and degassing, because of the solubility effect, drives us in this direction. So that vector is differentiation or melt evolution and water loss. So that's a very clear case for decompression crystallization. The melt inclusions themselves, I've shown two nice images here. Here they're associated with this resorbed boundary. This is a plagioclase. Can't remember the scale here, but that's a phenocryst. And we see very complicated zoning, and then a period of resorption, more calcic plage, shown with the lighter colors. And here are a whole bunch of melt inclusions that I analyzed. And we even get these rather fine tubules that connect somewhere in the interior of the crystal or in the rim to the actual matrix glass. And we've measured water diffusion along these. I won't talk about that today, but that's a nice way of getting an ascent rate, a degassing, related to degassing. This melt inclusion here is a nice regular shaped inclusion, or a little bit rounded, but you see it has a very complex relationship to the zoning in the plagioclase. The zoning actually wraps around the melt inclusion. And this is a feature of pretty much all the melt inclusions at Mount St Helens. And it tells us there's a rather complicated relationship between the growth of the crystal and the trapping of the melt inclusions. And they do appear to maintain some connection to the outside for some period of time, eventually becoming necked off or occluded by the outermost rim of the crystal. So I'll return to this zonation in plagioclase later in the talk, because we can look at diffusion timescales across these rims to learn something about that process of ascent and crystallization. So let's start with how the magmas were made, where they originated. So I've shown here, we can focus on three different arcs, but let's just stick to the cascades here. So these are two Harker diagrams showing the chemical variation in cascades magmas, the gray squares, from basalts with 10, 12% MgO, all the way through to evolved glasses and rhyolites. And we see that evolution in MgO and then again in alumina. And of course, in alumina, you get this characteristic peak that tells us the magmas were wet because plagioclase is suppressed and then starts to crystallize, bringing the alumina down. Conventional models of magmatic differentiation would describe that to something like fractional crystallization that involves a magma chamber in which crystals nucleate, grow, and then settle out. There are various reasons I don't think that's why magmas, how magmas differentiate, not least because we don't really have these large bodies of magma, certainly not sufficiently large to be imaged geophysically in arcs like the Cascades. So starting, well, it's really began with work with Steve Sparks and Katarina Nen in 2006 with some thermal models. And then these are dynamic models from Matt Jackson and Steve Sparks and myself. We looked really at the growth of a deep crustal or a mid-crustal mush in which the system is periodically replenished by basaltic magma from depth and evolves not so much by crystallization in a magma chamber, but as percolative flow, shown by the little wiggly lines, of buoyant, more evolved melt through a crystal mush. And so this would be what is imaged by geophysics. Melt fraction might be 10, 20%. And a very important differentiation process is that the melt migrates through the mush. Eventually, the melt travels at sufficient speed that it creates these porosity waves, and the most important porosity wave occurs at the top of the mush where the solidus isotherm occurs. So in other words, the melt is pinned here because the rock above is too cold to allow this process to continue. So this melt lens is occurring at the top of the mush. It doesn't have to occur at the top of the mush. It could occur within the mush, but a significant layer of silicic melt occurs at the top of the mush. What this means is that the chemistry of the melt is buffered all the way through this mushy region because it's interacting with a volumetrically dominant mush system. So the melt is evolving chemically by interacting with crystals rather than the crystals precipitating from the melt. At some point, we have sufficient melt, this is my melt lens in red here, that the buoyancy force is sufficient to exceed the strength of the rocks above. Now, of course, that can be facilitated by tectonics. There's some big faults around Mount St. Helens. But either way, this is where the melt departs from its source and begins ascent. And we call this the launch point. And the working hypothesis here is that the chemical characteristics of volcanic and indeed plutonic rocks are established at the launch point. This is where the chemistry is determined. The melt ascends from there up a dike at sufficient speed that very little further chemical differentiation can occur. That is not to say nothing happens. The magma crystallizes for the reasons I showed in the earlier slide. It degasses because the pressure is dropping, but it works really as an essentially closed system. So if we look at the chemical characteristics of volcanic rocks, we would imagine their chemistry tells us something about the point at which they were last in equilibrium with the mush. And because the mush contains many different mineral phases, this is a point of multiple saturation with a diverse range of minerals on the liquidus of a particular erupted magma. And we can use that as a very surprisingly precise barometer for where magma was manufactured. So this is a multiple saturation concept, and this is from something I wrote last year. It's evolved a bit in interesting ways that I'll come on to in a couple of slides. So let's start with a very simple approach using the Gibbs phase rule. We have 11 components, and the mush could consist of a large number of phases. In an arc setting, we might expect plagioclase, orthopyroxene, clinopyroxene, amphibole, hornblende, magnetite, ilmenite, a melt, obviously, and a vapor. So we would have, say, 8 phases. This is the schematic of the mush. The red is the melt. And so the melt composition would, at its liquidus, that is, at this point, have on its liquidus simultaneous saturation with all of these minerals. And if there were 8 of them, then there would be 5 degrees of freedom. And we can define those degrees of freedom as we like, but we could use pressure, temperature, the fluid composition, the redox state, and I've taken one compositional variable, potassium oxide. Obviously, if there's olivine around, we have fewer degrees of freedom. And if there's quartz around, we have fewer degrees of freedom. But this is the assemblage that I'm going to be talking about now. So we can actually find out where the magma was in equilibrium with all those phases in 2 different ways. The first is we can use the inverse approach. To do that, what we do is we take the magma, the erupted rock, and we subject it to high pressure temperature experiments with various amounts of water, conditions, redox conditions that we think are consistent with that magma. In an arc, that might be nickel-nickel oxide plus a log unit, say. And we hunt across the liquidus for a point where we have simultaneous saturation in 4, 5, 6 minerals. That's quite a painstaking bit of work. You have to do quite a lot of iteration between different experiments, but normally you can get there within about 15 to 20 experiments. And pretty much every arc magma is multiply saturated on its liquidus at some point. And I keep emphasizing that on its liquidus because we need to have all those minerals coexisting when the melt fraction in the experiment is about 90–95%. Every magma will reach multiple saturation if you cool it down to its solidus. That is meaningless in this context. And I'll call that the inverse approach. The forwards approach, which I've also used, is to take all the melting experiments that are in the literature and hunt for those that produce liquids similar to your target, in this case, Mount St. Helens dacite. And of course, what you do there really is you parameterize all of the compositional space for multiply saturated liquids. You parameterize it in terms of P and T, and you find out under what P and T and XH2O and so on, you have a liquid that is closest to Mount St. Helens dacite. So the inverse approach, a lot of experiments. The forwards approach, trawling the PETDB database. The reason we think this is relevant is that we do have samples of mush from all arc volcanoes, including Mount St. Helens. And these are xenolith fragments. They're about the size of a fist, maybe a bit smaller. And they contain a wide variety of minerals, sometimes in some complex textural relationship. And I show 4 of those xenoliths here. Perhaps in many ways, perhaps the most interesting is the top left here, because we can see the interstitial melt, interconnected interstitial melt. It's vesicular, telling us it was a hydrous melt. And it lies along the boundaries between the grains. You can see it as a thin film between orthopyroxene and clinopyroxene here, or around magnetite. This is melt that is moving through the mush, and it's chemically exchanging with the mush as it goes. So this is percolative reactive flow as a snapshot. If we look in detail at these textures, we find they're not a simple one-shot crystallization assemblage. There's a lot of textural complexity. In this one, for example, it doesn't show up quite as well in backscatter, but this medium to dark gray mineral here is amphibole. And here the amphibole is forming by reaction, and it creates big poikilotic plates that engulf the clinopyroxene and the orthopyroxene. And this is plagioclase out here. In this case here, we have some rather complicated reactions that may well involve oxidation, where olivine is in contact with orthopyroxene. And we get these wonderful symplectites at the interface. These are composed of orthopyroxene and a magnetite. In this particular sample, we have orthopyroxene with little Bleby-X solution of clinopyroxene, and we have freestanding clinopyroxene, which has itself exsolved, all surrounded by plagioclase. And finally, here's another example that shows olivines that are highly resorbed and wrapped in orthopyroxene. Here we can see olivines, and up here olivines. And this is the result of that well-known peritectic reaction. Olivine plus melt goes to orthopyroxene. And in fact, the hallmark of all of these reactions is they describe peritectic processes. And remember, peritectic processes cannot be achieved during fractional crystallization because you need to have a mineral to react with the melt to produce the new mineral phase. In perfect fractionation, you don't have any reactant early formed mineral to participate in the peritectic reaction. So most arc magmas lie along peritectics. We can't have peritectics during fractional crystallization, but we can during percolative reactive flow. If we interrogate the xenoliths for their temperatures, we find that the temperatures, depending on different thermometer methods, 2 pyroxenes, hornblende plage, magnetite, ilmenite, give a range of temperatures, but typically round about 900 degrees, 860 to 960 degrees. And that's important because that is lower than the temperatures at which these magmas were erupted. And what's significant there is that all of these melts, we can analyze intergranular melts or melt inclusions, they're rhyolitic or rhyodacite. They're more evolved than the magmas that erupted at Mount St. Helens, which remember are silicic andesites. So that's quite significant in terms of the plumbing system and its temperature evolution. Right, so back to multiple saturation. There are a lot of experiments being done on Mount St. Helens dacite, and the left-hand diagram there shows all of the experiments that are at the liquidus. So this is the liquidus surface. There are many more experiments, of course, but these are the black circles are experiments where the melt fraction is 95% or more. And the colored lines show the stability fields of the different minerals as indicated at the top. So if you like, that's a liquidus surface, and appearing on the liquidus surface would be magnetite outlined in blue, or orthopyroxene outlined in pink, and so on. And the multiple saturation field, where ilmenite, CPX, OPX, plagioclase, amphibole, and magnetite coexist, is labeled MSP. That's that sort of gray lozenge. That is where the Mount St. Helens dacites were last in equilibrium with the mush. That is their launch point, the point at which they acquired their chemical character. And we see that that MSP ranges from potentially from over 8 kilobars down to about 2 kilobars. We can put an added constraint on that because the plagioclase composition within the MSP lozenge is not everywhere the same. And I've contoured it here for plagioclase composition, the anorthite content, and we see it's anorthite 54 up here and 62 down here. And if we look at many thousands of plagioclase compositions I've analyzed from Mount St. Helens, there's a very distinctive peak here round about anorthite 60. So anorthite 60 meets the multiple saturation lozenge somewhere around about there. So that gives us a source pressure of about 4 and a bit kilobars, or a depth of 15 kilometers. You're already spotting that's exactly where the crustal conductor is. The plagioclase that's more sodic than anorthite 60 out here, these are all phenocryst mantles and rims that have grown during decompression. So that's the multiple saturation point. This is based on the inverse approach, 920 to 950, 3 to 5 kilobars, and not pure water, about 60 to 90% water in the coexisting fluid. That's the horizontal axis. If I use the forwards approach, so all the experiments that have ever been done on every magma composition, parameterize them and look for a multiply saturated liquid corresponding to Mount St. Helens dacite, and we can of course now extend this approach to all magmas, well, all magmas basically, but I've done it in the Cascades. The forwards approach, we get 950 degrees, 4.4 kilobars, 68% water in the mole fraction, water in the fluid, and a total water content of about 5.5 weight%. So that was what I did last year, 2 years ago. And together with Greg Weber, we've developed this to look more generally at multiple saturation. And the very interesting thing arises that I think reinforces the approach. And that really looks, again, we're looking at experiments. We've taken a machine learning approach, as I'll show you. But what we're trying to do now is understand the chemical diversity of igneous rocks and what that means in terms of the real number of independent components. So Gibbs phase rule would say, well, you've got 11 oxides, so there's 11 components. But we know that natural magmas don't occupy all of compositional space. We don't have magmas on Earth with 30% alumina and 10% silica. They can exist, they can make them in a blast furnace, but they don't exist on Earth. So what we did is we took, I don't know, there's probably about 50,000 magmas here, and we did principal components analysis on that magma composition cloud. And to cut to a chase, we found, that's what I'm showing here, principal component 1, 2, 3, and so on. We can get 96% of all of the compositional variation of all igneous rocks can be described by just 4 components. Now, those aren't unique oxides. It's not silica, alumina, and so on. It's some combination of oxides, and that's what this little principal component composition plot shows. Principal component 1 is some combination of everything. Principal component 2 is mostly sodium. Principal component 3, mostly alumina, and so on. So actually, the real number of components, the effective number of components in igneous systems is only about 4. So actually, multiple saturation no longer really needs 6, 7 mineral phases. You can get there with significantly less. And so what this means is that the multiple saturation concept can be really relaxed beyond the minerals that I outlined in the last slide. So what Greg did was took all of the experimental liquids, and it's quite a lot. I can't actually remember how many. And this is the compositional range of the experimental liquids, shown in the colored symbols, contoured for temperature. And in the background in gray are all the magmas, silicate magmas, I should emphasize, that have ever been erupted. And what we see is experiments pretty much reproduce the natural range. There are a few natural magmas that are not captured very well with the experiments. And these are the PT conditions of the experiments. We have regions that are very well represented and regions that aren't well represented. Water obviously depends on pressure to some extent. So some regions are inaccessible. And you can see that clearly here. We can't have experiments with very high water at low pressure. So we use the extremely random trees approach here to develop a machine learning thermohygrobarometer that is available. We haven't, the paper's in review, but the application is available online if you want to test it. It's called Magma Tab, and that isn't the point of this talk, so I'll just gloss over this, but we can achieve errors of about 1.9 kilobars, 39 degrees Celsius, and about 1.5% in water. The water, the hygrometry part, is not as good as it might be because we have rather few precise measurements on water contents in experiments at really low pressure. So that's a bit of a limitation. So this is a thermohygrobarometer that we can apply to any igneous rock, provided we think it was at some point a liquid. So that could actually be an erupted lava, or it could be a melt inclusion. And there are various different ways of running Magma Tab, but that will be a different talk. So we can also apply this same concept to all of the magmas erupted at Mount St. Helens during the 1980 to 86 eruptive period. So this is now a pressure temperature plot, and the red circles are the whole rocks from 1980 to 86, and that is the point at which they were multiply saturated with at least 2 minerals in the source region. And we get very, very consistent pressures of 4.5 kilobars, exactly the same as we had before. That's my MSP lozenge from previous slide. And that tells us that the dacite were all manufactured by a percolative reactive flow that became arrested at a pressure of 4.5 plus or minus half a kilobar, a depth of 16 kilometers. The melt inclusions record rather lower pressures, bit of a scatter, lower pressures and a big range of temperature. The lower pressure limit here is largely an artifact of the lack of experiments below 1 kilobar that we can use for training the barometer, but we see that the melt inclusions are clearly cooler than and less deep than the dacites themselves. So these dacites have ascended and they've crystallized en route. Sumit mentioned in the introduction some work I'd done showing that because magmas are ascending almost as a closed system relatively quickly, the release of latent heat of crystallization means that the temperature actually increases as the pressure goes down. The magma is actually getting hotter as a result of crystallization. And that can be on the order of 80 to 100 degrees because of the amount the magmas have crystallized. And that's these gray symbols here from a paper in 2010. I think it's 2006 actually, but anyway. And here we see melt ascending from here, starting to heat up. And I suspect this scatter in the melt inclusion data also reflects that latent heat of crystallization effect. a couple of other arrows in here that are worth mentioning. The first is that an adiabat would have a slope similar to the gray line. So running something like that, this slope is subadiabatic. Either the magma cooled during ascent or it cooled before it started its journey. And the xenoliths I showed you earlier suggest that cooling occurred at depth prior to the magma starting to ascend, which I think is quite interesting. We form that melt lens at the top of the mush. It has a dacitic composition. Then it starts to cool and crystallize before it ascends. It's doing that as essentially closed system, so it doesn't change the melt chemistry, but it means we have some deep-seated crystals. And so that's the cooling path, dacite manufacture, cooling of the melt lens, and then adiabatic ascent, melt inclusion formation, and some latent heat crystallization causing the temperature to rise. So now we're in quite a good position to compare that entirely petrological image on the left to the geophysical image on the right. This is from Carl Ullberg's work. So we're looking at a sort of it's kind of a combined VP-VS velocity variation tomographic image. Here is the region where the P and S waves are slowest, labeled dacite magma. Here are the earthquakes shown as little dots. Here's the summit. Some interesting things. I've put them on the same scale here. Where the petrology tells us dacites are manufactured, character is consistent with this region. The earthquakes root in this region, and we see earthquakes rather sparse down here, following what is called the conduit and becoming much more abundant at shallow levels. This is the magma starting its journey. This is the magma starting to degas, and we've got all sorts of rock fracturing because of that fluid release. So an incredibly good agreement between two totally independent images of a magma plumbing system. So this is a diffusion seminar series, so let's have some diffusion. This is the first of two types of minerals that we've looked at. Again, this is quite old data, and Ralph Doman was involved in this project. This is looking first at diffusion in orthopyroxene phenocrysts. So those are orthopyroxenes, and that's a false backscatter, false color electron backscatter image. And this is more magnesian, and red is more iron rich. And several things stand out. Firstly, the orthopyroxene is zoned, but most importantly, the zoning is rather diffuse in the core, meaning some time has elapsed, and is really sharp at the rim, meaning much less time has elapsed. So what we did, well, what Kate Saunders, who was a postdoc at the time in Bristol, did, is look at the time scale recorded by this outermost rim inner rim pair. So this interface just here. So we were looking to get a time scale from this region here. We didn't go for time scales in the interior, although we could have done. Bear in mind, some of these crystals in the interior may be very old. They might be crystals that grew in that accumulated melt lens at the top of the mush. So here's a chemical profile. We don't actually analyze it point by point. We simply use the grayscale, which tells us about the composition, and then we use a transfer function that relates grayscale to Mg number. And we use the magmatic temperature for this particular rock. Here's the diffusion path. We use titanium or aluminium to give us the initial condition. We get a step in those elements here. And the fitted diffusion path gives us a time scale for this outermost zoning, this one here, of about half a year, 5 months. And so we did that for, I think, many hundreds of crystals. I can't remember exactly how many. And so we said, we know the eruption age of the rock. Let's go back in time by the time scale given to us by the OPX and find out when something happened to the OPX to cause a change in the Mg number. So that could be a process such as degassing or mixing with another aliquot of magma, It could be latent heat release due to the crystallization of the surrounding melt and so on. And what we found is that we took crystals. So you take a crystal, say, from 1986, and you have a diffusion age from orthopyroxene that is 1 year. So that relates to an event in April 1985. If we took a sample from January 1985 and it gave a 2-year time scale, then that takes us back to January 83, etc. And so we found out where the peaks of events recorded by the OPX were. So these are perturbations to the magmatic system. And we found a cluster of events here and a cluster here. And the older cluster matches quite well the 1980 eruption. And the younger cluster matches a period in March 1982 when there was a swarm of deep earthquakes. So we think these crystals are recording an event that occurred in the overlying magma system, and then they erupted some months or even years later, carrying with them a memory of that perturbation. And that was something we published 11 years ago now. So that's the story from orthopyroxene. Let's look at the rather more complicated but more interesting story from plagioclase. So plagioclase has unbelievably complicated zoning, and I've shown a selection of crystals here that we've studied in detail. So these are backscatter images. Grayscale relates to a northite, lighter color, more calcic. Each crystal has a broadly similar characteristic, a hopelessly complicated core, in some cases such as this one showing some vestigial zoning, rather blurred, and corrosion. And that may well be a crystal that's surviving from the mush itself. A region around that's very spongy, full of melt inclusions, and shows a lot of evidence for disequilibrium, lots of mineral inclusions as well. And then finally, on the outside, some rims that are oscillatory zoned that go out to an outermost rim. And within this oscillatory zoned region, let me see if I can find a good example, we see some nice resorption horizons where we truncate earlier formed zoning. There's a truncation there, for example. And this zoning continues all the way out to the outermost rim. And the outermost rim of each crystal is the same as the ground mass. So this is recording the plagioclase leaving the source region, journeying upwards and doing its best to maintain equilibrium with the changing pressure, hence the changing water content, the changing melt composition due to crystallization, and also the temperature perturbations that arise due to latent heat release elsewhere in that little magma volume. So each crystal is trying to tell us a story about its magmatic journey from deep, presumably the core, to the point of quenching, the outermost rim. So we developed a method, this is with Oleg and Ralph, we developed a method to track the P, T, and melt fraction conditions that each crystal had experienced using microanalytical data on trace element and major element zoning. So to do that, we have to parameterize the experimental data from Mount St. Helens. There are rather more data than are shown on the left-hand diagram. We parameterized the pressure, and temperature, and melt fraction, and the anorthite content of the plagioclase, which is, of course, the main topic of interest here. So what we did is this is the composition of the plagioclase as a function of temperature for experiments done on a single bulk composition of Mount St. Helens dacite. And because there's very little evidence for magma mixing at Mount St. Helens, we are confident that that is the dacite that experienced closed system crystallization during ascent. And what we found is that the anorthite content correlates with temperature, but also with pressure. So this is the correlation at 125 MPa. This is the correlation at 200 and so on. So the anorthite content increases as the temperature goes up and increases as the pressure goes up for that particular bulk composition. So we take that parameterization and we then analyze crystals to see what path they may have charted through PT X space to produce the observed zoning. So let's take as an example this little yellow transect here. It shows a change from anorthite 55 to anorthite 45. These are my contours of anorthite content, increasing with temperature, increasing with pressure. That's the liquidus, that's the solidus. We could achieve AN 55 to AN 45 by isothermal decompression or by isobaric cooling. So in that case, we can't deconvolve those two rather important changes. But what we then did is we superimposed on that the amount of melt in the system, the liquid fraction. And the liquid fraction of these blue contours, so obviously the liquid as it's 1, the solid as it's 0, and I've shown representative 40% melt, 60% melt, and 80% melt contours. And the reason that's important is this trajectory from the last slide gives us the AN zoning 55 to 45, but very little change in melt fraction. This profile gives us the same zoning change, but a big change in melt fraction from 60% to 40%. So if we can actually recover the anorthite content and the melt fraction, we can actually work out whether we were cooling isobarically or decompressing isothermally or something in between. And we get the melt fraction by looking at trace elements. If we know the partition coefficients well, we can look at the chemical evolution of the melt and relate that to changing melt fraction as recorded by the plagioclase. And to do this, we need to pick elements that only go into plagioclase that are unaffected by the pyroxenes and magnetites and whatnot. So the elements we picked of most interest were strontium and barium, and of course the anorthite. Now we used the ion probe for this. Now the problem with SIMS is that the spatial resolution is not good enough for what we want to do. So we modified the technique to do what we called high resolution SIMS. We didn't do kinetic energy filtering of the secondary ion signal, which meant we had much higher transmission, and we were able to work at 0.02 nanoamps, achieving a 2 micron spot. And so we were able to measure strontium, so in red, barium in green, and anorthite in black on a traverse. This is a kind of 2 segments of a traverse from the core to the rim. So this is the input information that we're going to use to reconstruct pressure, temperature, and melt fraction from individual crystals. And then we'll come to using diffusion of these signals to tell us something about time. So I did this for a bunch of crystals. I can't remember, maybe 10. It's quite a lot of work. And because it's 10 minutes for each analysis point. And we developed what we called uncrystallization modeling. So what we do is we take our parameterization, we start with the rim, and we work back from the rim to the core, making a change in P or T or F to simultaneously satisfy the anorthite content, the strontium content, and the barium content, assuming simply that we have an aliquot, a finite volume of magma that's remained a closed system. So we take the compositional zoning that we've measured, we assume it's chemically closed on the scale of, say, a thin section or a hand sample. We assume that each layer has grown at equilibrium, so interfacial equilibrium. Obviously, the whole crystal's way out of equilibrium, or it wouldn't be zoned, but each layer has grown in equilibrium with the melt. And then we ungrow it. We know the partitioning of strontium and barium. This is work that Ralph and I did a few years ago. And the nice thing about strontium and barium partitioning, it depends only on the anorthite content and the temperature. Some people would try to tell you otherwise, but I'm pretty sure it's only the anorthite content and the temperature. We've parameterized the plagioclase composition as a function of the anorthite content, and we actually use the calcium content as well, because we need that to get at this. So that's an additional parameter that we take from the experiments. We've parameterized melt fraction in terms of temperature and pressure. We assume that the co-precipitating phase doesn't contain any of the elements of interest, so we don't have to worry about alkali feldspar or something else crystallizing. There isn't any. And we don't have to worry about magnetite or orthopyroxene because they don't contain these elements. We start with a bulk reference magma based on the average whole rock. We take the temperature at the rim, so where we start the uncrystallization, we say we know the temperature from the eruption temperature. We uncrystallize from rim to core, and we do a full mass balance at each growth increment. So we are solving simultaneously for pressure, temperature, and melt fraction as we move towards the core. And then what we recover from this method is the pressure, the temperature, the melt fraction, the amount of plagioclase crystallizing, which is another important variable, how much strontium was in the melt, and how much barium. And we ground truth our modeling based on the many analyses of melt inclusions I have. So that's the process. I'm happy to explain it in more detail, but that's how uncrystallization works. So let's take a single crystal. I can't remember which one this is. But what we find, using only the plagioclase, is that here's the rim. It's quite shallow, pressure in MPa, that's a kilobar. The core is quite deep, but in this case, about 250, 280 MPa. So higher pressure, a drop in pressure, spending time at lower pressure. The temperature starts cooler in this case, rises, and then wiggles about a bit, and this is the eruption temperature. The melt fraction, for the most part, is dropping. In other words, the magma is crystallizing, but there are periods corresponding to resorption where the melt fraction goes up. In other words, the crystal is resorbing and then actually no longer provides a record as it's resorbing, and it starts to grow again. And we see that early on, the crystallizing assemblage is about 40% plagioclase and then rises to about 80%. And that's this transition from the competition with amphibole early on to being basically plagioclase and orthopyroxene. So just to emphasize, this is a totally independent way of getting temperature and pressure. And you'll have spotted that we're still getting up to 280 MPa. Some of these crystals, as you'll see, go up to about 400, a bit less than 400, which is where we think the magma started. So each crystal is recording a journey from the melt lens up to the surface. And they all look like they start the journey somewhere between 11 and 15 kilometers depth. Okay, so that's a single crystal. Let's now look at a bunch of crystals, 4. So maybe 10 traverses across 4 crystals. So the crystal cores, this is a pressure, temperature, and pressure melt fraction plot. They all start somewhere up here, and they end up somewhere down here, and they all make their way somehow, mostly dropping pressure and increasing temperature from about 400 MPa to about 100. At that point, we don't have the spatial resolution to analyze the outermost rim, and this technique no longer works. I've shown the melt inclusion data, temperature, pressure, from a previous slide from that paper in 2006. And we see an incredible overlap, again, completely independent records. The crystal decompressing and crystallizing, we see it here, decompressing, the melt fraction goes down, decompression, crystallization, starting at the source depth and progressing all the way up through this vertically elongate system that I showed earlier. So plagioclase and melt inclusions tell a coherent but slightly different part of the story. Melt inclusions are from about 220 MPa to virtually nothing, to the ground mass, whereas the plagioclase record the deeper part of the journey. Right, those of you who wanted to see a bit of diffusion need wait no longer. So the great thing about these two elements, particularly strontium, in a diffusion context, is strontium evolves in a completely different way during crystallization to how it does during equilibration. As a plagioclase grows, it starts anorthite rich, calcic, and it becomes anorthite poor, sodic. And that means its partition coefficient gets progressively higher. Because strontium is always compatible, as it's growing, the strontium in the melt is going down. So as you go from anorthite to albite, the strontium content during growth becomes progressively less. But because the partition coefficient is higher in albite than it is in anorthite, if you leave that crystal for a very, very long time, the trend, strontium anorthite, will change from having a negative slope to a positive slope. So just to make that point, this is D-strontium plagioclase melt versus anorthite. It's around about 6 or 7 here, sodic plage. It's around about 1 down here. So the strontium all wants to sit in the sodic end. But as the crystal grows, it's removing strontium from the melt. So the growth trajectory looks like the red line. Re-equilibration looks like the black line. Time rotates this vector. So what we'd expect to see is if we have an old part of a crystal, it should have a negative slope, and a young part of the crystal should have a positive slope. We can do this with strontium, not so easily with barium, because in barium, the partition coefficient is always low. So crystallization sends barium up, and equilibration moves it in the same direction. So strontium is uniquely placed for this particular calculation. Right, so here are the data for those 4 plagioclases, and I've separated cores that are in solid symbols from the mantles and the rims, the outer, the oscillatory zone bit, they're the open symbols. And what we see is that the open symbols show the positive slope consistent with growth and very little equilibration. The cores show positive slopes, actually steeper than we would expect for reasons that will become clear, consistent with partial equilibration. So we have old cores and young rims. Not really a surprise. So let's now look at the core, let's call this the core mantle interface. That is going from that rather, this calcic region here surrounding the resorbed core. I'm going to look at that interface where my cursor is here. So this is one crystal. Again, I can't remember which one. Here is the core. Here's the mantle, so the innermost rim. And the anorthite is shown in black. And the strontium is shown in red. Now, the strontium shows a diffusive slope across this region here. And we interpret this diffusive slope to be the diffusive relaxation of an initially steep profile, which we obtain from the growth zoning based on the uncrystallization model. And we have some time that has relaxed that interface, and different time calculations are shown 330 and 100 years. And that slope is consistent with a time of around about 30 years. Any longer, and we're starting to lose that coherence with the data. So in other words, about 30 years elapsed between the core becoming mobilized, perhaps interacting with some melt that was starting to move, and getting entrained in the ascending magma. So we could consider that to be a rejuvenation timescale on the order of about 30 years. The cores themselves appear to be close to equilibrium. Actually, as I said before, the strontium and northite variation is actually in this crystal is a bit steeper than we'd expect for equilibrium. That's the black line. But still, it's a very distinctive negative slope. The rim is a very distinctive positive slope. So we have old cores that appear to have been at or close to equilibrium, so more than 1,000 years old. The cores started to interact with melt. That's probably the percolating melt moving through the mush. The system becomes reactivated on the order of 30 years before eruption. And the core is therefore much older than the rim. And a very nice piece of work by Carrie Cooper and Mary Reed from 2003 showed from U series that individual plagioclases are a mixture of very old cores based on radium and almost zero age rims. And that's consistent with what we see here. So now the last part of the story, let's just look at that rim. It's clearly hopelessly out of equilibrium. So what we've done here is we've taken the zoning. So this crystal here, this is the innermost rim. So from 300 to 240 microns from the crystal edge, which will be over here. And then this is the next segment. So this bit here would sit over here. Same crystal. Growth, equilibration. What we did here is we took the observed zoning pattern, which is shown as the dots, and we said, how long could that survive at magmatic temperatures? So it's a zoning survival time calculation. So we don't have to make any estimate about the initial profile. We simply say, how long could you preserve the gradients, those wiggles? And what we find is not long. So we take the inner part of the crystal, so the black are the data. After about 0.1 years, we haven't deviated much from the data. By 0.3 years, we're now starting to lie outside the range of the data. After a year, we are significantly outside the range of the data. What that means is that complex zoning could not have survived for more than a year, possibly not much more than 4 months. The outermost rim, we get even less or even shorter survival time. The symbols show the data. 0.1 years is in black, and we're already starting to get some deviation from the data. So the survival time of this outermost rim is less than about a month. What that means is that the crystal rims are really, really young and grew during decompression that took place relatively shortly before the eruption. The magma could have stalled and got stored somewhere, but not for much more than a month or so. So the rim growth took place after the magma left its launch depth, and that all occurred less than about 4 months before the eruption. So we've now got timescales that are commensurate with volcano monitoring. We can calculate a growth rate. It's about 2 times 10 to the minus 8 millimeters per second, which suggests a fairly steady undercooling of about 10 degrees based on kinetic experiments on plagioclase crystallization. And these timescales are some hybrid of the ascent and stalling. That is, pausing at some shallow depth before eruption. So that's really all I have to say. So let's see what we've learned from this natural laboratory. So the magma system is vertically extensive. It's probably very broad at the depth of the mid-crustal, lower crustal conductor, where there's a lot of partial melt, but it's connected to the surface via pipes up which magma flows. The magma itself was generated by percolative reactive flow in a hot zone at about 16 kilometers depth. This hot zone is where mantle-derived basalts are intruding and driving the heat. and the melts percolate through that. The source temperature is about 960 to 1020 degrees. But based on the xenoliths, and in fact, the uncrystallization modeling, the ascent journey didn't start until the magma had cooled quite a bit below that. And I think that's the time after which the melt lens accumulates, that it cools, and then the magma starts to ascend. And that may be the time required to perhaps exsolve some volatiles that drive extra overpressure. Phenocryst growth is driven by rapid near adiabatic ascent and degassing. Some other work I'm doing with Oleg Melnik, I won't talk about that here, suggests that because these magmas are very, very buoyant and relatively low viscosity, ascent rates are on the order of centimeters a second. The magma stalls at about 6 kilometers, and it could spend months there. And it does that because crystallization increases the viscosity, and the magma tends to get stuck without a bit more of a push from below. Crystallization during ascent, and perhaps during stalling, causes the temperature to rise by up to 100 degrees. We can use individual plagioclase crystals to recover detailed ascent histories. That is to say, each crystal can be used to tell us something about a particular PT trajectory. And perhaps most interestingly, if we're looking for rejuvenation of a system, we want to look at the deepest earthquakes. We're learning nothing from this little lot. We want to look at the deep earthquakes. Deep VT, we need to precisely locate them. And in this case, these events, this is from the PNSN catalogue, they're all routing round about where the source is. And there's a nice sequence of earthquakes from May to June 2016. This is a package of earthquakes occurring in 1 month, and we see they run from about 12 plus or minus 2 kilometers to about 3. And that is probably a little squirt of magma coming from the source zone and ascending into the stalling depth. The volcano didn't erupt in 2016. That magma probably got to the stalling depth and just died. It solidified. Okay, so I'll stop there. I've really no idea what time it is. But that's a sort of a summary of 33 years working on Mount St. Helens. And thank you for your attention.
Thank you, John. I mean, 33 years seems to be the number of the day today, 30 years or so. Yeah, it's good that we had you together alone today, because we got a nice summary of the background on Mount St. Helens, the machine learning tools, and how one gets the different conditions, and finally how one can relate diffusion chronometry and the geophysical methods to get some timescales. And I think a very important point is that you get many different timescales, and one needs to interpret them and relate them to the actual volcanological processes and that different timescales relate to. So what that also means is it's a lot of food for discussion and question, and I'll let you get a drink and catch your breath and see who wants to ask a question or start something up. Lidrick.
Yeah, can you hear me?
Yeah.
Yeah.
Hi, Lidrick.
Hi, thank you very much, John. I enjoyed both sections of the presentation. It was very interesting. I have several questions. I will start with some questions on the uncrystallization modeling that I really liked. I was wondering if there why do you have different estimations of the melt fraction from the first figure, where you would just consider the anorthite percent, where you wonder if you have cooling or decompression. And in that slide, I think you say between 60 and 40% of melt, but finally your estimates are between 90 and 60% of melt fraction. And for the same story of related to uncrystallization, I'm wondering why in this nice model you only consider the plage, because strontium and barium are mainly incorporated in the plage, I agree, but they are fully incompatible or almost fully incompatible in the other minerals which are still crystallizing, and it may influence or it could influence the melt composition and thus the model's results, isn't it?
Yeah, so in answer to the first question, the difference, maybe I should share the screen again, you can see what I'm talking about. So in answer to the first question, the reason it looked different is that I just picked an arbitrary starting point here, AN 55 to 45. Whoops, sorry. I could have picked a different starting point and we'd have a different melt fraction consequence. So if I'd started up here, it would have been starting at 40%, AN 55. If I'd started over here, we'd have had about 70%. So these were just illustrative. So there's not necessarily a relationship between this plot and here we've got slightly different. We go to AN 62 in this crystal and down to AN 35. So that's why the melt fractions looked different. In answer to your question about other phases, you're absolutely right. Amphibole will contain some strontium. The budget of strontium is dominated by plagioclase. I have assumed that all the other minerals have d-strontium of 0, and that isn't correct. And to some extent, there's a little bit of a fudge in there, which is the proportion of plagioclase crystallizing. So the bulk partition coefficient that controls the melt evolution is d-strontium at a given anorthite and temperature multiplied by the fraction of plagioclase. And so I recover XPL from the modeling, and what isn't plagioclase is some other mineral. And if that other mineral is amphibole, then some of the strontium could be going into the amphibole. But overall, d-amphibole is so much less than d-strontium and amphibole, so much less than d-strontium and plagioclase, and there's so much less amphibole, it didn't make a lot of difference.
Okay. And can those other minerals affect the melt fraction you have estimated?
Yes. So there's the melt fraction that we estimate does not correspond to the plagioclase fraction, meaning some other minerals are also crystallizing. So if I go on, yeah, you can see that here. So the melt fraction here is 87%. Of the crystallizing phases, this is the plagioclase fraction of the crystallizing phases, only 30% is plagioclase. So 70% of what's crystallizing at this interval is not plagioclase. Out here, 80% of what's crystallizing is plagioclase, and the other 20% is probably orthopyroxene. What it means is that these calculations are much less reliable here for all the reasons you're saying, because there are other minerals crystallizing.
Okay, thank you very much.
Thanks, John and Ludwig. A quick comment to everyone. You can type in your questions in the chat as well, and there are comments coming in and so on. So you can type things in there, but while you're waiting for those, Adam.
Thanks, Sumit. Hey, thanks, John, for a great talk. I just sort of have a general question that I wonder if you'd be interested in addressing. You know, the first half of the talk looked at an equilibrium thermodynamic approach, and then in the second half of the talk, you showed us pretty abundant textural and compositional evidence for the importance of kinetic processes. So I'm wondering how you reconcile both of those.
Yeah, so the first part of the talk is about long-lived equilibrium processes that give rise to a melt lens that has a chemical composition that's in equilibrium with the surrounding mush. And that probably takes place on timescales of thousands, maybe hundreds of thousands of years. Then what happens is we take a parcel of that melt and we subject it to very, very rapid change. And during that rapid change, it can't fully equilibrate, but we achieve interfacial equilibrium at each stage. In other words, the plagioclase rim layer that grows is in equilibrium with the surrounding melt. What I haven't considered is kinetic fractionation of the elements. So if the crystallization is really fast, then the partition coefficients that we're using aren't really appropriate. The way we test for that is we get melt inclusions and coexisting plagioclase, and we analyze them both, and we see whether the partition coefficient matches the prediction, and it does. Certainly for strontium and barium. Rare earths, I'm not so sure. So we're probably crystallizing on a time scale that allows strontium and barium to partition at equilibrium, but probably not really slow diffusing elements like the rare earths.
Okay, thanks, John.
If I may comment on that, that's actually something you can test and check, because we have a growth time for the outermost rim of 0.1 year. And you can work out whether basically strontium and barium in melt would diffuse away fast enough to maintain equilibrium.
Yeah, that's a very good. I haven't actually done that, Sumi, but yes, that's a really obvious thing to do, isn't it? Yeah.
So, other questions or comments? If I'm waiting for others, I was intrigued. Ludwig, I'll just get to you in a minute. I was going to ask something that I got thought about. So, so I was thinking about the machine learning part that you did, and actually, it's very nice to see that you get 3 or 4 principal components, because the thermodynamic components, of course, are the linearly independent ones. Even if you have 11 oxides, it should be the minimum number that you need to describe the system, and so 3 or 4 or something, some much lower number makes sense there. But what I was wondering was that in this large body of experiments, one of the things that we've had problems with in experimental petrology is that many of the old and even the newer experiments didn't characterize the iron 2 and iron 3. And that, of course, plays in a big way into calculating magnesium numbers, for example, where you use only iron 2 plus.
Yeah.
So, and in terms of the intensive variable, it relates to the oxidation state, which relates to dehydration and everything. And I was wondering if you had thoughts on that, how much it does or doesn't affect the extraction of data out of that.
That's a really good point, Sumit. So let me be clear. I haven't considered ferric iron because, for the simple reason, as you say, people haven't measured ferric iron. I could use Crescent Carmichael if the experimental FO2 is known. Sometimes it isn't, of course. And I could estimate the ferric iron in the glass. And that is an additional component. In looking at all of the natural rocks, there are analyses of ferric iron. So I probably could consider that as an additional component and just use the subset of wet chemical data where we know ferric iron. I think worst case, we may end up with 5 principal components rather than 4. But to me, the real surprise, I mean, I don't know about you, but I've been sort of chasing 10 space or 11 space for the last 30 years, thinking, well, if we want to reduce the variance, we need a hell of a lot of phases. I don't think natural igneous systems have very many degrees of freedom, which is probably rather obvious when you look at the fact that they occupy a tiny part of compositional space. And it makes you wonder whether it was really worth doing all those experiments in simple systems where you genuinely have, if you're in CMAS, you definitely have 4 degrees of freedom. And I think the reduced number of effective components in igneous systems means that there's a lot of scope for barometry and thermometry that exploits that. And I think it explains why there are whole sort of family of new mineral barometers that use just one mineral. And that shouldn't really work if you've got an 11 component system. But actually, because your number of components in the melt is much less, and because the partition coefficients for major elements between minerals and melts probably don't vary much, I have a feeling that's why these thermometers and barometers that should not work from a thermodynamic point of view actually seem to work quite well.
Well, some of the barometers are based on exchange reactions, so they are based on just those components. But it is a very good example of how, we petrologists have partitioned ourselves into igneous and metamorphic petrologists, and then think about it differently when we do the things, because what you just said is the basis of the metamorphic phases concept, right? I mean, that's what Escola came up with, that you see repeated assemblage. You have many different components in a rock, but you still see repeatedly the same assemblages, and these must be in equilibrium, was the thinking at the time. Yeah, so it's a variant of that idea again. But what I was thinking was not so much the number of components, but if you change the FO2, Fe2, Fe3, you can change the crystallization pathways, the sequence of minerals that form, for example. So a simple extreme case would be if you had a lot of iron 3+, you could end up producing pure phosphorite. You do actually at Stromboli. So that kind of thing. So,
well, again, what we'd have is we'd have a mush that has some sort of redox state, and the melt, because it's typically a more evolved melt, is percolating. It doesn't have much iron, and it's percolating through a system that contains all the iron, all the ferric and the ferrous. So it's probably the redox state of the mush buffers the redox state of the melt. So I liken the mush. Well, I used to like, maybe this isn't very appropriate, but I used to liken it to the communist state. So however different you were at the time you entered the mush or the communist state, by the time you came out the other end, you were pretty much the same, because you were completely, I'm recording, I think. You were completely controlled by your environment. So if you introduced into the mush a really, really oxidized melt, it wouldn't survive very long, because it would have to share its electrons with the entire mush. And it also means that even if you have little bits of exotic material in mushes, like bits of sedimentary rock, they don't really change the phase relations of the mush system very much, because you've got this volumetrically overwhelming amount of mush and probably a small percentage of melt at any one time.
Yeah, well, over time, probably the melt imprints its properties on the mush as well. So they come to it's a kind of a titration process, right? I mean, you're titrating the melt through the mush. So
that's exactly what it is. It is a high temperature melt titration process. You feed something in the bottom, and then it makes its way up.
Right.
And the mush has a buffer capacity. You can exhaust the buffer capacity, of course. If you keep exploiting the same path, it no longer has to react with the mush, and that may be very important. You also could completely make over the mush to a new assemblage. So if you put enough oxidized stuff in the bottom, you will eventually oxidize the mush. And it's kind of interesting. I showed some pictures of those rather unusual symplectites that I suspect are the result of oxidation of something passing through the mush and oxidizing the olivine where it meets the magnetite.
Yeah, I mean, it relates to the narrow compositional space we were talking about earlier, I think. So I have a question related to that as well, but Lidwig had a question. So Lidwig.
Yeah, thanks again. Yeah, I come to my question, but just to follow up on what you just said, I totally follow you that the mush matrix, which is percolated, could buffer the system, but we should keep in mind also that most of the systems we are looking to are open systems, which are fed almost continuously, maybe not continuously, but at least oscillatory, in an oscillatory way. So finally, even if the melt fraction is small in the mush, the reactive porous flow, the chemical composition of the bulk system could be also, at least sometimes, governed by the melt, because you are percolating a lot of melt during a lot of time. But it was just a comment on that. My question is related to the latent heat of crystallization you spoke about. I was very, very interested in that. But I am not sure to fully understand it. There's one stuff I don't understand. In fact, when we crystallize, we release some latent heat. And one possibility would be to reheat the system. And that's what you see. But that's the point I don't exactly understand, because if you release some heat, you have one possibility, which is to reheat, to increase the temperature, but the other one is just to decrease the cooling rate. And you see the reheating, but I don't understand why we reheat, because to my mind, if we start to increase the temperature, the increment of crystal we have just crystallized is supposed to be dissolved again. And we cannot continue at this increment to crystallize, to release another step of heat and to increase the temperature, because at the next step we'll again dissolve it. So that's why, to my mind, but I'm looking forward to see how you see it. To my mind, when we have this release of the latent heat of crystallization, we should just decrease the cooling rate, and otherwise reheating itself should dissolve the stuff. So what do you think about that? Sorry.
Well, you're absolutely right. Apart from one thing, you're losing the volatiles. So the latent heat of exsolution of the fluid from the melt is pretty small. The volatiles, because not much is coming out, so a small amount of volatile, 1% of water comes out, that changes the liquidus temperature quite significantly. But if you remove that water from the system, it doesn't change, doesn't take much heat with it, a little bit. So what I've got is think of a closed vessel with some melt in, and I'm going to move it from pressure 1 to pressure 2 being lower. I'm going to release the water, let's call it water, that's exsolved, and take that out of the system. So at that point, I've now increased the liquidus temperature. I'm driving crystallization. That crystallization drives, releases latent heat. So the easiest way to think about it in terms of that sort of loop you're talking about is we rise up to the new condition. We crystallize 20% because we're undercooled. 20% crystallization is about 50 degrees of cooling. But once heating, 50 degrees of latent heat. So now the temperature is going to go back up 50 degrees. So I don't have 20% crystallization anymore. I've only got 15. Yeah. So then I'll do the same thing again. So in nature, what probably happens is you over crystallize and then you rein it back because you've now got hotter than you were. And there's this rather complicated feedback. But the key answer to your initial question, how does the melt do it? It's because I'm removing the bubbles of water at each stage.
Okay, very good. Thank you very much. It means this reheating stage, increase of temperature, could exist only in a decompressing system, isn't it? If we doesn't decompress, we are unlikely to increase the temperature.
Let's say we take a completely dry magma, it'll be the situation you just described. We will just cool more slowly. So if I take a body of rock at some temperature and it's losing heat and it starts to crystallize, that latent heat of crystallization will just slow down the process of cooling, which is why intrusions take longer to cool if they're crystallizing. So everything you said, yes, but for a decompressing magma that's losing a volatile that profoundly affects the phase relations, then you can have latent heating in effect.
Thank you very much, John.
Thank you. That's a good explanation. And I think it's important for many of the listeners here on the forum. So the other question I was going to get to was, if you have this percolating melt through the mush zone, so I'd imagine there'd be a lot of local variation if you look at individual melt pockets at instantaneous times. And there'd be two signatures of that. One would be in the different melt inclusions, and the other would be in the instantaneous zoning profiles you produced in the minerals. So because we are interested in the minerals, I was wondering, do you see signatures in all the melt inclusions that you look at, that there's a lot of variability?
Stuart, that's a great question. The short answer is yes. So what's remarkable about these systems? So let's take Mount St. Helens. I could think of other examples. When you look at the melt inclusion record, there is a staggering variety of melt inclusions because they're trapped at various different points, and they may be trapped actually in the source region itself. So a lot of xenoliths, for example, have quite evolved melt inclusions, suggesting that they once got down to quite low temperatures. The melt inclusion record then is really, really diverse, and that they relate either to the ascent path or to the accumulation of melts from very different provenances that accumulate in the melt-rich layer. So another good example, Greg Weber and I published something looking at strontium isotopes, and the strontium isotopes in plagioclase cores from really big eruptions in the Altiplano are incredibly diverse. They're totally out of equilibrium, apart from at the rim. So you get the sense that magmatic systems are made up of different components that had spent all their life totally separated from each other in different bits of the reservoir, more radiogenic, less radiogenic, what have you. And they come together in a melt lens for a pretty short amount of time, and then off they go. Mm-hmm. So in the Atana eruption in the Altiplano in Chile, the amount of time these very different plagioclase cores can have spent together is probably on the order of a few years. So they have a really complex, heterogeneous history, and then a relatively brief amalgamation, and then eruption. Mm-hmm. So it's exactly what you said.
Yeah, I mean, what becomes very important is in terms of interpreting the zoning profiles, because on the one hand, you have a lot of big chaotic mix. On the other hand, you have a lot of information sitting there waiting to be read. Mm. So, Alan, you have a question. Alan?
Yep. Can you hear me?
Yeah,
I can hear you, Alan. Hello.
Hi. So I have a question. Your talk about this latent heat effect, can that be responsible then for producing these resorbed surfaces that you see in phenocryst?
That's my feeling. I think, as in my answer to Liderik, I think depending on the feedback, we've not really looked at this in any detail. I think it's a very interesting problem. You can imagine the system over crystallizing, then the temperature goes up, then it thinks, oh, I've got too many crystals now because I'm 20 degrees hotter, and then it resorbs some of that crystallization, then it starts again. So even though the process of magma ascent could be smooth with degassing all the time, you get this. It used to be called, it's a bit like what Allegra and Jopard years ago called constitutional undercooling. It's essentially the same thing. You grow too much crystal, in this case, because the system has forgotten about the latent heat release, then it gets hotter and it has to digest some of that crystal. Mm-hmm. And as I'm sure you know, Alan, a lot of this oscillatory zoning, you see a growth zone, then it becomes resorbed. Sometimes it's very hard to see, but it's sort of eaten back a little bit, and then you get another zone. You get this sawtooth pattern, and that's very characteristic. And I wonder if that's a latent heat release effect.
Well, that's interesting, because that also would imply that a lot of these, obviously, you can also get resorbed surfaces through magma mixing.
Indeed, but those plagioclases, I couldn't tell you how many zones, but let's say 300 zones.
Yeah.
And
That's not gonna happen
we
for
know
you.
the crystals are young. The process I'm describing is it could be a very fast feedback. 100 magma mixing events is just not really an option.
No, I suppose not. So yeah, thanks for the information. That's interesting.
Yeah, I mean, it's a part of a bigger scheme of things. I think that oscillatory systems are much more common in nature than we probably have considered them until now, because you have interactions between, and in this case, between thermal and processes which react on different time scales.
Absolutely. So you've got these two
Right.
things going on. You've got diffusion of the chemical components that you need to grow the crystal. You've got the diffusion of the volatiles that need to make the bubble to then get out of the system. So it's the permeability of the magma is also important because the volatiles have to leave. Then you've also got the rate of heat diffusion, either from the surrounding minerals into the volume or from the volume of interest out. And that's a really complex interplay. I think it would make a very interesting theoretical computational study.
Well, you have a third one there because you pointed to the role of viscosity. So that's a mechanical one.
Yes.
And that acts on a different time scale yet. So you have three, thermal, mechanical, and chemical.
Yeah.
So I'm talking about that because I'm preparing a talk where I'm trying to put that together.
Well, this may be an example of that. I've just said, should I answer the question in the chat, because it's actually to me, it's not to everybody. So
well, I don't see that question. Yeah,
no, you
go ahead,
won't.
please.
So Hadi Obrami asks me directly, what's the link between amphibole decomposition and complex zoning with melt inclusion in the mantle towards the rim of plagioclases? It seems where we can see melt inclusion in the mantle of the plage, it can be related to amphibole decomposition at 10 kilobars and 900 degrees. So 10 kilobars is much deeper. I don't know whether you meant 10 kilobars, Hadi, but the amphibole decomposition is actually another interesting part of the story. And kind of in answer to Liederik's questions earlier about amphibole, I have conveniently ignored amphibole. And as well as amphibole taking some of the strontium, amphibole is resorbing, and it's actually increasing the melt fraction by a process that doesn't really involve the plagioclase at all. And I'm sure you'll understand. I can't get amphibole into this model as well. It becomes terribly complicated. So there is an important role that amphibole decomposition, dissolution plays in all of this.
Mm-hmm. Ralph has a question.
Yeah, so I'm thinking about this cooling stage in the source region that you were mentioning or thinking has happened. So any information, the minerals that we can use to reconstruct it, because the plagioclase core, according to the crystallization model, has also is at the lower temperature end. It doesn't reflect the higher temperatures that you initially had. I was thinking about maybe orthopyroxene has this long zoning, maybe normal zoning, so that maybe is something that could reflect this cooling stage, or what do you think?
Yeah, the cooling stage is something I only really came across relatively recently. So I've used this sort of multiple saturation barometry, first this thing I call Chompy, and then subsequently this machine learning. And, and initially you get two temperatures, you say, well, 970 and 900, they're about the same. But I found they're always out. The temperature at which the xenoliths are stored and the temperature of which the magmas are in equilibrium with the mush seem to be about 70 or 80 degrees out. And then I looked at the plagioclase zoning, what you're just referring to, and that also gives you these lower temperatures. And it looks to me as though I could imagine a situation where you first accumulate the melt lens, and let's say it's now got its chemical composition, it's at 1,000 degrees. But in order to become truly buoyant, it now needs to crystallize perhaps 10%, so that some volatiles exsolve, because we now, we could probably achieve water CO2 saturation. some crystals actually grow during that phase. So we accumulate melt, we grow 20% crystals, and then we start the journey upwards. And it might be that melt itself isn't quite buoyant enough. We need to get a little bit of volatile out there. Or it may be that the melt lens takes a while to accumulate, but it seems to be cooling before it begins to ascend. I think what would be interesting, Ralph, is to look at those cores of the OPXs that I showed that Kate Saunders didn't look at. They might be, I mean, I have no idea. You can probably tell the age just by looking at them, but they're pretty diffuse.
Yeah, that would give relatively long time scales. I mean, I cannot give a rough estimate here, but more like, I mean, the short zoning that we modeled, which would take months, no, or about a year, then this long zoning would definitely take thousands of years or so, I would guess.
Yeah,
I tested that.
So I think that actually might be something. Maybe we can write this up. We've only been doing this for 10 years, but it might be interesting to have a look at the OPXs and maybe even look at some trace elements as well as MGFE. I see that you've recently confirmed that the iron magnesium diffusion coefficients that we used are about right. So those are quite robust timescales, I think.
I think we have not fully resolved. We have got new data and that shows some strong compositional dependence, but this seems to be also decreasing with temperature. So probably we are about right, but at this stage we cannot completely confirm that. Probably they're not very far off for sure.
Okay. Yeah.
Mm-hmm. So another question on the chat on Paul. So wait a second, I lost it. Yeah, there. Paul Rene asked another amphibole question. So. Might amphibole decomposition increase pH2O, inducing plage resorption?
Well, amphibole only contains 2% water, and these melts already have about 5 or 6. So actually adding the amphibole back doesn't really, the amphibole has less water than the melt it's dissolving in. So it doesn't have a particularly big influence on the water budget. I should say as well, there's not an awful lot of amphibole in these rocks in the first place. So I don't think it has a huge effect on volatile budgets or even trace element budgets, but it could have an effect.
And there's a related question on the chat from Hadi again, whether the amphibole decomposition can increase the oxygen fugacity and oxidize the olivine to see reaction reams around olivine.
Yeah, that's an interesting question. Again, there's not a lot of amphibole. If you dissolve amphibole in these melts, unlike what I said about the water, the amphibole has got a lot of iron and it's got a lot of ferric iron. So amphibole decomposition could contribute to the overall redox of the system. I'd be quite interested to look at those symplectites. Some of them are really quite spectacular, and there may be some information, some diffusive information that we can get on the zoning across the oxide orthopyroxene interface. I've no idea whether that's an old feature or whether that's something that happens shortly before eruption.
I'm looking back into a very distant memory here, but there's a ancient work on some gabbros in Norway, metamorphic rocks, where they looked at olivine orthopyroxene coronas to look at oxidation state, I think.
It's a good memory. It's Johnston and Stout, about 1980, during my PhD, about 1986.
That would be right, yes.
Now, they call them orthopyroxene magnesiopherrite.
Okay, yeah. Mm-hmm.
These are not magnesiopherrite. In preparation for this talk, I went back and looked at the data. These are titanomagnetites. Now that's odd, because in the Johnston and Stout work, it's quite simple. It's essentially FMQ, right? You're taking olivine and then you're oxidizing it and you're producing not Q, but OPX, and you're producing magnetite.
Mm-hmm.
But these magnetites have got lots of titanium in them, and there isn't any titanium in the precursor olivine. So it's a bit more complicated. You've got to get the titanium from somewhere. So I think Johnson and Stout's coronas, which is my first port of call when I saw these textures, I think they're a closed system, solid state process. This looks like it involves mobile components, titanium, for example.
If you have a melt, that would do the silica activity as well as the titanium.
I think that's exactly what I think. So we have a system now, whereas it was previously, it was olivine and combining with oxygen to make orthopyroxene and magnetite. Now we have an open system where we have a change in the silica activity and a change in the titanium activity, and the rum products involved reflect both of those changes. So that's yeah.
So that'd be cool to model.
Indeed.
Okay, and we're nearing the end of our actually full seminar, and so that's good. We've had a long, good discussion, but are there other questions, comments? And you can just speak up, Lyric, yeah.
Sorry to monopolize a very short question. I'm looking forward to see the MagmaTab paper. If I well understood the figures you've shown, this nice calibration is based on the tolytic series. And I was wondering two points, because I'm now working on alkaline series, and I was wondering if you think it's easy to extend it to alkaline series, or if everything has to be redone for those series. And second, if you expect that it will be the same components, or if you will need more components to account for those alkaline or very alkaline series.
Okay, well, actually, the first thing you said, Lyric, isn't correct.
Okay.
So it works for all systems. We've used every single experiment ever done.
Okay.
Now,
Perfect.
that said, there are a few gaps in the data set. So there aren't that many experiments done on alkaline systems, peralkaline systems, pantellarites, the kind of weird, funky stuff. We don't have a lot of that. We're lacking granites at high pressure, so low temperature, high pressure systems. And we're lacking really reliable measurements of dissolved water in melts below a kilobar. And I've got a postdoc starting soon to try and fill in the gaps. So that's the first bit. In terms of the number of components, so that's now a different database. That's, believe it or not, that's every single volcanic rock in the GeoRock database. That's probably 100,000 analyses there. And we don't make much effort to filter the data. That's just everything. But they're just volcanic. And those four components, notwithstanding what I said to Sumit about us ignoring ferric iron, they apply to everything. I mean, I think it's kind of obvious to everyone. Perhaps it should have been more obvious to me. Igneous rocks just do not occupy all of the compositional space they do. They could. And that means that the number of degrees of freedom of igneous systems is much lower. And it doesn't really change even in well, carbonatites would definitely be different. I haven't put carbonatites in there. But other than that, all these systems occupy a really limited component space.
Mm-hmm. Yep. Makes life somewhat easier.
It does.
Asta, yes, go ahead, please.
Yeah, I have a question in general related to diffusion chronometry. Like most commonly, like the zoning in plagioclase crystals implies about different magmatic conditions, and during the ascent, it gives a time scale of like days to months. I'm working on the dike swamps in Deccan Volcanic Province, so it's during the Cretaceous Paleogene boundary. So I'm thinking to use this diffusion chronometry for my dike samples, where I'm looking many of the zone clay phenocryst. So can this diffusion timescale can be useful, like how it can be used, or
Yeah.
like will these timescales will be useful in any way to get about the magmatic process?
Right. Well, there are a number of important differences and some important challenges you're going to face. So I'm very lucky with these crystals that I was able to measure the strontium and the barium zoning. Now, if you have access to laser ablation or to some analytical technique that allows you to measure the trace elements across your Deccan plagioclases, that could be very useful. So that's the first thing. If you can't measure the trace elements, you're always left with this ambiguity that an orthite can change as a result of temperature or as a result of pressure. That's the first reason I was lucky here. The second reason is that there are so many experiments on Mount St. Helens that I can develop a parameterization of the phase relations in response to changing pressure and temperature. There's much less done on the Deccan experimentally. That said, the Deccan is basaltic, it's pretty dry, and this is an environment where the MELTS software works relatively well. So you might be able to use the MELTS software to give you the phase relations. So that's a very long answer. The short answer to your question is yes, there's no reason you couldn't do this with the Deccan, but you need trace element zoning and you need to be able to parameterize the phase relations, and then off you go.
Yeah, I'll just add that MELTS will probably work pretty well with the Deccan basalts. And yeah, trace elements are always useful.
Yeah.
So,
Yeah, thank you very much. I will try to.
The other way you could do it as to actually, given that you can, so MELTS is really powerful. I only don't use MELTS because I need a level of precision for this project that I get from experiments that MELTS couldn't give me, particularly wet amphibole bearing systems. What you could do with Deccan that would be quite interesting is you could take MELTS and you can actually, you can drop the pressure and drop the temperature. You can follow different paths in MELTS, and you could probably track the changing composition of the plagioclates, as you go. So you could actually do a series of forward model numerical experiments and see whether you get anything that looks reasonable. So start with MELTS. Imagine you're in some source region, wherever you think it is, and say, right, I'm at 1150 degrees, I'm 5 kilobars. Now I'm going to use MELTS to track an ascent path in which I cool a certain amount and I travel at a certain rate. You could do it in an isenthalpic way, an isentropic way, and you could track the changing plagioclase composition and keep doing it until you get a result that matches your crystals. I'd like to be able to do that with Mount St. Helens, it just wouldn't work. But that might be something worth trying for basaltic systems.
yeah, so I was just going to say we haven't done this for a cooling or a decompressing system, but we did something very similar in the Carl et al. Paper in Journal of Petrology, where I put it on the chat. So
yeah, I've seen that. Yeah.
Well, I shouldn't say I, because well, Marin ran a lot of MELT simulations and produced the entire population of plagioclases and actually all the other minerals that one could produce. And so there's a bit of a discussion in there as well of what we call, population-based whatever thermobarometry or determining the conditions of rocks. So yeah, you could look into that.
I'd forgotten that paper. So is that for Mount Etna?
That's Mount Etna, yeah.
Yeah, that's quite a powerful tool. If you have confidence in MELTS, then actually you could run those calculations. And then obviously going back to Asta's question, you then need to do the diffusion chronometry. All you've got is the pressure and temperature now that matches the plagioclase zoning. Then you need the trace elements to get the time scale.
Yeah, so the story there is, so now we're over time. So I'd like to just thank everybody for being there. And if you want to stay on, stay on, but because it's very good discussion. But what I was going to say was that the good news about those basalts was that since then we've done a whole bunch of experiments actually for completely different reasons. And they seem to work pretty well, give the right olivine compositions and so forth. Because Mount Etna, you can just take the exact composition and stick it into a furnace and control oxygen fugacity and do the experiment. So that works pretty well. Now, the trouble with plagioclase is that it's quite very sensitive to the water content. And that's something you cannot handle that well. So that's, degassing and all of what you've been talking about goes and affects the anorthite content of the plagioclase as well. So that's why, trace elements may be useful because, the anorthite content depends on pressure and temperature, but also the water content quite strongly. But, try it and see what comes out. You have to play a lot with melts and something, but it's worth the shot.
Yeah, absolutely.
Okay, so like I said, we are over time, so it's very good to have had all this discussion. And we are going on a summer break because next month we have the Goldschmidt conference and everybody will be busy with that. And in August, nobody wants to sit around and listen to talks. So we will be back with a new set of talks in September, I hope, or latest by October. And in the meantime, everybody have a good break, a good conference, and join us back in. And thank you, John, for taking the time, not just to prepare the talk, but for all of this discussion.
Well, discussions work if people ask questions, and I really appreciate all those excellent questions. And I hope that will kind of prompt me to write this stuff up. I know Ralph hopes it'll prompt me to write it up. He did so much work on this, and he's thinking, will it ever see the light of day? Okay.
Okay, so the quick answer to, there's a question on the chat. How can I access the link to the lecture? That's on the website. I don't have the. Julian, do you have the website on the?
I think the link is also sent with the email when you register it for it, no? I think there's a link. There's a link. Then when you receive the confirmation that you registered for this talk, then there's also a link to the I think to the recorded talks. I think.
If you all stay on for just a minute, I'll put the link on the chat right now. I'll just go on the web and find it and put it on there, just so you can get those.
Is it?
Just a minute.
Or maybe the initial Linda sent it.
Yeah, it's come up. Julian sent it.
Okay, yeah, so I put it as well.
Yeah, but it's also so it's the announcement of Linda's of the talk by Linda. There you find also a link. So in the announcement sent out to people, there's also a link for the recorded talks.
So now you have it multiple ways, and a lot of congratulatory notes for you, John. So thank you again. Okay.
Okay. Well, thank you very much.
Bye, everybody.
Bye bye.
Bye.